A gravitational wave has been detected. It's been labeled as GW150914. And what we want to look at here is compare the power in that gravitational wave, and we're going to find out that it exceeded the power output of all the stars in the universe, but it did that for a very short period of time of about 20 milliseconds. The news release on this was a Caltech news release that appeared on the 11th of February of this year, 2016. Today is the 24th of March. The publication appeared in Physical Review Letters on the 12th of February, and that was by Abbott et al. And the title of that was Observation of Gravitational Waves from a Binary Black Hole Merger. And that detection was made by the LIGO system, LIGO, and LIGO stands for Laser Interferometer Gravitational Wave Observatory, LIGO. There's two of these systems. One is in the state of Washington, the other is in the state of Louisiana. And each one consists of two interferometer arms, each arm 4 kilometers long. And the signal that was detected looked something like this: strain over here, frequency going this way, time going this way. This is a time axis. And what I'm indicating here is roughly the frequency in this part of the signal and the frequency in this part of the signal. So when it started out, it was roughly around 35 hertz, and it built up to 250 hertz. And the time involved there is on the order of tens of milliseconds. Now, you can take this data. What they did was they took this data that they measured, and they fit it to field equations with different changes in the parameters to figure out what the distance was to where the two black holes merged and what the masses were that were involved in that merger. This change in frequency of 35 to 250 hertz, that's a chirp, referred to as a chirp, frequency chirp. I won't try duplicating it by whistling, but it's just an increase in frequency. So if you look at this as frequency and this as time, it would look something like that, which is what you see here: low frequency starting out to a higher frequency when it ends. And Professor Charles Meisner, he came up with an interesting name that he suggested for this chirp, and he calls it the Hallelujah chirp because people have been waiting to see it for such a long time. So what we want to do is calculate the power in this merger of two black holes. First, actually what we'll do, we'll first calculate the energy, and then we'll compare that to what's released by all the stars in the universe. So there was a black hole with a mass of 36 suns, and it merged with a mass of 29 suns. So these two black holes were orbiting one another. As they got closer and closer, they were orbiting faster and faster, and that's what you're seeing here in this extremely rough sketch of the actual signal. Higher and higher frequencies, and then eventually they merged. So we have 36 suns merging with 29 suns mass-wise, and you would expect that to give you a much larger black hole with a mass of the sum of these, or 65 suns. But that's not what happened. The resulting final mass was 62 suns. So 3 suns were converted to energy. So the implication is that the equivalent mass of 3 suns was converted to energy. And that energy went into the gravitational wave that was detected. So to calculate that energy, all we need is the famous equation, E equals mc squared. And if we substitute in, we have the mass of 3 suns. So we're going to have 3 times the mass of the sun. It's roughly 2 times 10 to the 30th kilograms, but the actual number is something like 1.9891 times 10 to the 30th kilograms. So that's the mass of the 3 suns that were converted to energy. Then we multiply that by 3, roughly the speed of light, 3 times 10 to the 8th meters per second. And that's squared. And if you work that out, you get 5.4 times 10 to the 47 joules. What we want to do is we want to calculate the power of the merger. This is the energy that was released. That energy was released over a short period of time, so the power of the merger would be equal to the energy that was released by converting 3 suns to energy divided by the time that it took. That's joules per second, so that gives us watts. So in this case, we have the energy divided by a time, and that's roughly 20 milliseconds. So that's 20 times 10 to the minus 3 seconds. So we have joules over seconds now, and that is equal to watts. And that will equal, you work this out, and you get 2.7 times 10 to the 49 watts. So that is the power of the merger of the 2 black holes with the equivalent of 3 solar masses being converted to energy, and that the time it took for that energy conversion to take place is roughly 20 milliseconds, and so that is the power that we calculate. What we want to do now is calculate what is emitted by all the stars in the universe. So we'll start out over here. There's roughly 100 billion stars per galaxy. 100 billion, that's 100 times 10 to the 9th, so that's 10 to the 11th stars per galaxy. And there are roughly 100 billion galaxies in the universe, so that is also 10 to the 11th galaxies now. We'll just write it as galaxy over 1 universe. So that gives us the number of stars in the universe, and what we want to do is convert that to power. And what we'll do, just as an approximation, we'll say that 1 star produces as much power as the sun does. And the sun produces 3.83 times 10 to the 26th watts. So we have 3.83 times 10 to the 26th watts. So now if you work that out, you will get approximately 4 times 10 to the 48th watts. That's the power produced by all the stars in the universe. And what you can see is we had calculated the power of the merger of the two black holes to be 2.7 times 10 to the 49 watts. So this is all the stars, the power for all the stars. So if we divide these two by one another, you can see that we get roughly a factor of 7. So the power produced by the merger of those two black holes is 7 times greater than the power emitted by all of the stars in the universe. Fantastically large number. But again, the power that was emitted in that merger was only over a short period of time of 20 milliseconds, whereas this power emitted by the stars is going on all the time. Now this number is a little on the low side, because if you look at the number of stars as a function of their brightness, it kind of looks something like, very roughly speaking, looks like that. Brightness is going this way. So it's kind of like a absolute magnitude scale here, and the sun is here. So there's more stars that are fainter than the sun, and if you do this with greater accuracy, the number works out. Instead of being 7 times, it's roughly 50 times. So just to summarize what we showed, the merger of the two black holes produces a tremendous amount of energy. It lasted for 20 milliseconds. We convert that to a power. We compare that to the power emitted by all the stars in the universe. And we can see that the power generated by the merger of the two black holes is significantly larger than the power of all the stars in the universe.